Hello, 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 hello. Am I live? Am I live? Am I live? Yes, am I live? All right. So today we are gonna go with DS and Algo, and uh, we were doing what? Um, well, let me check about. Okay, wait, okay, wait. So I was learning linked list. Okay, and I've covered single linked list, double linked list, but I was working on the circular linked list. Okay, so we will start from circular linked list today. So let's read this book. Um, Circular linked list and single linked list has a double and a doubly linked list. The end of list are indicated with null value. Yep, but the circular linked list do not have ends. Okay. While transversing the circular linked list, we should be careful, otherwise we will get transversing the list infinitely. In circular linked list, each node has a successor. Yes, every node has a successor. Alright. Now note that unlike single linked list, there is no node with null pointer in the circular linked list. In some situations, circular linked lists are useful. Yep. For example, when several processes are using same computer resource CPU for the same amount of time, we have to assure that no process accesses the resource before all other processes do. Okay, that is Robin round robin algorithm. In circular linked list, we access the elements using the head node. Okay, we have the head, and for readability, let us assume that the class name of circular linked, okay, not a big deal here. So counting linked list, okay. So how it is working here is we have a single linked list, let's say, and the end of this single linked list, I mean the tail of the single linked list, singly end of the singly linked list is not null. Instead, it is connected with the head itself. All right, that's the most important part. But how to do this? How to do this here? So we have the node here, and in each node we have data, next and previous. But we have to we know that every okay, so node could be null, okay, but the circular linked list has the head that is, let's say it is right now it is null, okay, the tail is null, but when it exists, we make sure it has the head and it has the tail, and the tail's next node is the head. All right, so that's the whole story around it. Okay, now how to connect this? Okay, let's go to this here. Let's ask Grok. Okay, uh what is what is it? How do we implement circular linked list? All right, let's hear from Grok. Okay, the last node's next point to the head. Yep, no null at the end. So we do not have to mess with the null and we have to be careful about this. All right. Now the core rules is this: tail next is head, first thing. Second thing, hell head is null, that is empty list. Okay. And use do while to transfers. Okay. So we have the node data null next. Okay, so we are not okay. So the circular linked list would have would will be two types. Okay, the circular linked list would be of two types. Okay, that means when if I'm going through one direction, that is singly circular linked list, and if I can access from both the side, I mean if we can go from either the side, then we have doubly circular linked list. Oh my god. 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 Okay. Okay. So this is singly circular linked list. All right. So this has a head and it has a tail. All right. Head and tail. Okay. Since this is not a s- uh, doubly linked list, so it has no brev. Okay. All right. Cool. Cool. And now the length is 0. Okay. Now, what do I do when we append it? Okay. So let me do my own calculation in the copy. All right. So, um, so how it goes? If there is no circular linked list, it is a null singular, null circular singular. What I'm saying, singly circular linked list. Let me write it here. Singly circular linked list. All right. Now, if there is no head, okay, so let me write it. Append, append. Okay, so we have to put the data in here. That is a number. That is a number. And if this dot head, there is no head in here. Okay, then what do we do? We will do uh, this dot head is equals to, okay, we can do like this, const new node is equals to new node with this number. Oops. This, oh shit, this data, oh my god. Now if there is no head, then we will let this new node to be as this head of this singular linked list. Okay, this is not it. Okay, and what we do is this dot tail dot next next is equals to this dot head. Is it is it fine now? I think this dot tail would also be new node. Mhm. And then the tail dot next is equals to head. Is it okay now? Hell no. Hell no. And if not else, if not this, if we have like let's say if we have uh, a head and a tail and a tail and we append a new node in here. If we append a new node here, then what we'll do is what we'll do is let me think. Head, tail, new node. All right. Head is connected to tail, tail is connected to head. Okay. So what we do is we connect the tail to new node and new node to head. Okay. So this dot tail dot next. This dot tail dot next is equals to new node and then new node that what the heck next is equals to this dot head. Is it? Okay. Tail is this. All right. Are we good? Are we good here? Okay, so this dot tail dot next equals to new node. Uh-huh. And this dot node dot next is this head. And then this dot tail is equals to node. What the heck? What are you doing here? Wait. Okay. Now we have to update the tail. Correct. Yep, I got it. For updating, update the new tail. Okay. Got it, sir. Got it, sir. Let me display it. How we display this? Okay. Append display const. Uh, okay. So if there is no this dot head, then return no linked list string. We have to return it in a string. What else we have to do? We have to initialize a empty number array and we have to initialize the current head. Okay, okay, let me do this. Const vals, that is a number of array and that is this array, and then let current is equals to this dot head. Okay, then what to do? We go with two while loop. All right. So first what we'll do? We'll do uh, current is equals to current dot next. Is this something like this? No, no. Vals dot push. Vals dot push current dot data. Current dot data. Then we have to uh, current is equals to current dot next, is it? Yep. Current is equals to current dot next. What is going on here? Okay, current is equals to current dot next, and then we do while what? Current is not equals to this dot head. Okay. Current is not equals to this dot head. Okay. So what is happening in here is we are displaying it in a string that how would a circular linked list appears as a string. All right. So because we have in the linked list, so it has like the structure of the linked list would be like very nested. All right. So one list, and in that list, it has next, and that on that next, it has another linked list. So it's a very nested kind of object, you can say, kind of. So we don't want that object. So we wanna show every value in one string, that what are the things on there. All right. So we are checking with this do while loop, and we are checking first if the current, that means this dot head, if it is not equals to this dot head at last, then we would do this thing, this one and this one. That means we would push the current data to this array, and then it will do what we'll do. We will move the current to current dot next. All right. Now I will return the files dot join with what, this thing. Let me copy this entire thing. All right. So if I let's say if I import this one here, new circular. Oh my god. Export circle linked list. All right. And if we append 2 into it, and let's append some more values in here. Let's say 4, then 1, then 0, and I print the display list. All right. So I run run. What the heck? What the heck is going on here? Export name this not found model this. Is it? Is it? Is it? Export class. What is saying? Export name circular language is not found in the module. Zero circular language. All right. Zero circular language. It is in there. It is in there. Oh, there we go. So we append 2, then 4, then 1, then 0. Correct. And you can see 2410. That's it. That's how it works. That's how it works. All right. All right. Now we'll try to uh, do this in the reverse way. I mean, we would append on the beginning. I mean in an insert in beginning. All right. That take the data which is in the form of number, and what to do, we check that if uh, this dot head, I mean not this dot head, then we what to do, we do the same thing which we did here earlier. Okay. Uh, const new node is equals to new node with the data, and else what to do. So let me think here. What to do? So we have to add another head here, which is a new node. All right. So what I do is we link this new node dot next. What I do, that new node dot next, sorry, next is equals to this dot head. And then this dot tail is equals to new node. And now we have to update the head also, right? This dot head is equals to new node. That's it. That's it. That's what we need. That's what we need, I guess. Alright. So if not this head, oh shit. I could have did this one also. This dot append then the data. Alright. That was cool. It was cool. It was cool. Return. Alright. Now new node this, then this dot head is equals to node. Then okay, so we have to increase the length also. So am I right here? We are doing node dot next equal to this dot head, and then we are assigning the head to this node, and we are assigning the tail to this node. All right, very good here, very good, very good, very good, very good. And also we have to do this dot length plus plus, and in here also this dot length plus. Okay, we can do it here. This dot length plus. Mhm. Okay, cool, cool. We are good here. And then if we want to remove the head, it is so easy, I guess. Uh, it is easy, I guess. So if you want to remove the head, what you do is we are gonna pointer the tail to the head next. That sound very confusing, really. All right, we okay. Let's do it here. Oops. Remove head. Okay, so if wanna okay, so remove the head. How do you remove this head? Let's say okay, so what do you do here? Uh, remove this head. If no, this dot head, then return it. Okay, and if there is head, then what do you do? If there is head, then what do you do? Is this dot tail dot next the this dot tail dot next is equals to this head dot next. All right, and we have to make the new head. This dot head is equals to this dot head dot next. That is it. I think this is it. Oh dang. Oh dang 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 dang. Okay, let's see it's working or not. All right. So right now head is 2, right? And if we call here list dot remove head here and we print it in here. All right, it's working. It's working, yo. It's working. Let's see what's happened in here. This time the head has not removed here because there is no tail. All right. No, there is tail, but I think something is happening in here. So here, what is happening is if the length is 1, then okay, so that we null the head and null the tail. All right. And otherwise, what I did in here, and eventually we have to decrease the length. This dot length minus minus oops. Okay, if this dot length is equals to 1, then what do you do? Else what do you do here? We do this, and if this dot um head is equals to null and this dot tail is equals to null. This is it. This is it, guys. This is it. 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 Okay, we are good. We are good. We are good. We are good. All right. So another thing is to remove any value. Oh, okay. Let's get some position. Okay. Get oops. Get value at position. Uh, oops. Position, which is a number. Okay, which is a number, and then this position this number. So okay, so there are some condition which we have to check. If what if the position which I'm looking for is not there? Okay, so let's say if the length is 0, okay, and the second thing is we are not finding, like we are finding between the start and the end, not negative, not the like over exceed the length. Okay, have to check both two things here. So if not this dot add, okay, then we return it here. And if okay, so we can do here all the things, or position is less than this dot length, or 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 no, position is less than 1 and this dot length, if the position, let's say if they ask for 2 and I have the length 3. Is it okay? Let's see. Let me check once. Okay. The index always should be less than 0. Okay, index should not be less than 0. Uh, and index, I mean this position, uh, what are they saying here? Index is greater than or equal to this dot length. Okay, okay. I have to check the false one. All right. So what I'm saying here that if the this thing happen, is it not good? Okay. If the length is less than the position, then it have to return it. Or else position is less than 0, then I have to return this. Okay. Else you are fine. Else you are fine. Else you are super fine. Okay. So let's let current is equals to new. Uh no, current is equals to this dot head. All right. Now what are we gonna do here? We have the current. Now we will iterate the list. Okay, one by one, one by one. Okay, let's use two while loop. Okay, two while. Uh, so in this while, what I do is the position is less than this dot head, or position is equals to, oh sorry, uh, position is equals to this dot length. Redo current is equals to current dot next. This is it. Are we good? Are we good here? Are we good here? Okay, so they are doing I is equals to 0 and I should be less than the index. Okay, let's see. I think I'm good also. That position should be this dot length. Oh, sorry. So in this condition here, what is gonna happen is the condition is gonna check if it is true. Then, if it is true, then the do will go. Otherwise, the do would not run. Correct. So what we do here is position is this, and then oh sorry. Something is bad here. 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 Okay, something is bad here. Like we have to, let's say, let I is equals to 0. Okay, and then we're gonna check whether this I, and then we would move the I plus 1. Correct. So let me ask this here. Gemini here. Is this condition correct? I guess it is pretty correct. I guess it is pretty correct. But let's get a validation from it here. No. What the fuck? No. What did they say? Okay, so this is my critical bug. Start with start head button current I before checking. Before check-in runs at least one. Okay. You do current equal to correctness first, so I is equals to one. Means second node, not position one. Corrected words would be this. While this I is less than this, current equal to this. Okay. So two would go at least once. Correct. That's the that's the problem here. That's the problem here. That's the problem. All right. Let's make it near. So while I is less than position, current at correct next, and then I plus plus. That's the correct answer. Okay. And this uh return shit current dot data. Is it? Mm, let's check it out here. And what will do? Uh, get position at 3. OMG, no. Uh, const position is equals to this. Position 0. What the heck is it? Let's say 1. Oops, that's working you, but it has starting with an index with 0. That's interesting. That's interesting. No, but like if I think from the view of the length, then that is wrong, correct? Because in the one position, the two will be there. Okay, so let's ask him this: is it starting from the zero? I mean, when I ask for the position, no. There's a bad code right here in here, I guess. No, it is good. I mean, when I ask for the position zero, it is giving me the first position. Let me see live what I'm doing here. What I'm doing here. How do I see myself in YouTube on the small screen? What? Getting you. View your channel. I'm live, baby. I'm live. Okay, that's cool. That's pretty cool. Okay, so what it says, why position zero first node? Okay, zero first index is start and array is zero for okay. Then linked list position zero head and the program language C plus. Why is saying the entire concept for this zero thing? Okay, that means I'm good here. Okay, so if I can do a get value, then I can also do the remove value from the position at this position. Okay, so what I have to do is, let's say if I get the current here, and now I wanna remove the current. Okay, so what I do here, current dot previous. Okay, so we don't have previous right here. We don't have previous. We do not have previous in here. So how do we do this? How do this? Okay, so we can do one thing, like we can, how do you remove from the position, from at some position? How to remove the number at some position? Okay, I mean, how to remove the node at some position? So if we get the current node, uh-huh. Okay, so what we can do is, let me do this right here, right now. Yank it, then paste it, then remove at position. Okay, so we have the current here. So what I do here is that, mm, current, and then we have the the bridge, the end bridge. No, what do you call this? mm, to join node is equals to current dot next dot next. This would be good, I guess. Oh my god. Current dot next because we are removing the current dot next. Correct. We are removing the current dot next. Okay. So I got the current and I got the node that is next of the current next. All right. Now what will I do is I will join the current with the to join node. All right. And do I have to do something? No, I guess. So there are two connection in here. Okay. So I have to null this. I mean, if I override this, then it is okay. How Grok does the same thing? Let's see, 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 let's see. Remove the number, okay. Current and then previous is node or null. OMG, there are a lot of things going on here. There are a lot of things going on here. Okay, so I was wrong. So we have to remove the current, I guess. We have to remove the current, okay. So we are initializing a previous, that is a node, and then what are you doing here? That I'm assuming this previous is equals to current now, okay, and then current is equals to current dot next, okay, and remove function. We are removing the removing the current, right, right, and how? Yes, yes, we will remove the first node with that value. Let's walk through it how this works. Okay. Now, uh, okay. First case is remove the head. What are they doing here? Why are they removing the head? Okay. So they are removing the value, not the position. I wanna remove the value at some position. Then how would I do this? Okay, alright, alright, alright. Okay. What's going on here? is that we're on the position 0, then we remove the head, transfer the node before 1 to remove. The previous is this dot head, this dot head. Okay, the previous is this dot head, and let I is equal to 0, position less than previous equal to, okay, so I'm going -1. All right, so I got the previous thing. I got the previous, I mean the current and the previous. All right, and now the current is equals to previous dot next. Okay, that makes sense. That makes sense. And now we remove the value is equals to current dot data. Current dot data. Now we are bypassing the node here. That previous dot next is equals to current dot next. Okay, the previous dot next is not the current, but the current dot next. Okay, and removing the tail is if the current is equals to this dot tail. What is going on here? If removing tail, update the tail. So if current is equals to, okay. So if the current is the tail, then what we do is this dot tail is equals to the previous. This dot tail is equals to previous. What does this mean? Okay. So if you're removing the tail, then it has to be current, correct? And we are removing the current, so the tail is to be updated, right? And the tail would be previous because the current is not there anymore. All right, that makes sense. That makes total sense. All right. So what I guess from here is what I what I what I what I what I what I mean get it from here is I even didn't read all of these things here, but I code it and myself and understand how it works, how the next and the previous and the shit and how to travel through the node and everything. I did it myself, so it's more like it's the conceptual things which I would read here. I get more from doing this thing. All right. So now get circular circular linked list. Let me get push here. Oh shit, I didn't get at all thing. Get commit, get push. All right. So now let's read the docs here. I mean book here. All right. So inserting a node at the end of the circular list. That means we are appending this. Okay. So are done. We are done here. Inserting node at the front of the circular list. Yup. We have inserted the node in the beginning. Deleting the last node. Okay. We just saw that how to delete the last node. Okay, by doing previous and then current, and then we remove the current and we just uh, make the tail to the previous. That's it, deleting the first node in the circular list. Yep, we can do this also. Now here comes the Java code. Okay, so I don't really know Java, but I can still read this out, and like it's very similar to the TypeScript, I mean JavaScript. And yep, I don't have to read this also because I have done it by myself. And here we go. Okay, so the memory efficient W linked list. Okay, so I had read this article before how to use this W linked list with memory efficient by 60% I guess, and something is like that. And so it's a Sinha, some kind of Sinha journal. So, but it was some, I don't know what was that, but basically it was doing the concept was similar to the array things, like uh, how we find or how we like get the particular element of the array is like we are multiplying the bytes and the index and the like what was that? Oh shit, I forgot that. I have written this. I've written this well, I've written this, but I don't know where I've written this. Okay, so in this array we have the base address, and then we have the index. Okay, and we have the bytes, like each of 4 bytes, and the base address. Let's say we are starting from the base address of anything, and then each element has 4 byte, correct? So the address would be increasing by 4. Let's say if the address is starting at the 0, I mean 0, then the next address will be 4, and so on and so forth. All right. So how we find the exact, I mean, I mean, like how we find the element by its index is we multiply the, mm, we multiply, like we add the base address and we multiply the size and the index. Right, size and the index. Okay, okay. Size is 4 byte, and the index is the particular index which you want to find the number of the element is. Okay, all right, all right. So same kind of list, like uh, they basically remove, like in this linked list we have a previous and next. Okay, and I think they has written there that they had 8 bytes and 8 bytes of each, like each pointer takes 8 byte and 8 bytes, means 16 bytes. So we have to remove this 16 bytes and we just keep a distance, like this is the head, and that's it. And if you want to like go to some distance, so we can like travel through the distance. Okay, we do not have to initialize every time the next and the previous pointer. All right, so that's how we reduce that. Okay, so if we got read the journal as well, journal journal as well. All right, but there's no time because I've read it already. Okay, so okay, there we go. The pointer div is pointer plus to the previous node and the pointer to the next node. Okay, and this is the exclusive or. Okay, XOR. Okay, okay, they have shown here that how it works. Yep, look, the list node has the data, and the private list node list there is a list node which is the pointer div. Okay, pointer div. And what is the pointer div? Is the pointer div is the pointer to the previous node XOR with the pointer to the next node. All right, but I actually don't understand what's going on here. Okay, 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 okay. So let's read this. The pointer div pointer field contains the difference between the pointer to the next node and the pointer to the previous node. The pointer difference pointer field contains the difference between the pointer the difference between the pointer to the next node and the pointer to the previous node. I don't know what's going on here. I don't know actually what's going on here. The pointer difference is calculated by using the exclusive OR operation, okay? So the pointer diff of the start node head is the XOR of the null and next node to the head. Similarly, the pointer diff of the end node is the XOR of previous node to the end node and null, is it? So this is another subject to read. It's at own. Okay. So as an example, consider the following linked list. Okay. Now in this example above, the next pointer of A is null, XOR B. What the heck? The next pointer of A is null or XOR of B. Null XOR B. The next pointer of B is A XOR C. Next pointer of C is B XOR D. Next pointer of D is C XOR null. Okay, I think I'm getting it. I think I'm getting it. But partially. So next pointer of A is null and B. So like XOR works when like, let's see, XOR gate. Or not, let's read from here. XOR and computer science. Computer science. Oh my god, gigs for gigs. Oh my god, medium is down, bro. Medium is so down. Better we upgrade from this year. Okay, so the XOR gate sometime EOR or XOR is pronounced as exclusive OR. Okay, so the truth table is if I have 0, 0, then 0. If either of these things are true, then true, and both are true, then it is false. Okay, so it's work with exclusive OR. Okay, that means if it is an OR, like if it is one is true, then it is correct, and if both is true, then it is false. Okay, got it, got it. Now, what's going on here is a different situation here. Okay, so we are uh, Okay, by Prakash Sinha. Okay, let's read it from here. Okay. In the cost to make the small device cost-effective, manufacturer often need to think about reducing the memory size. One option is to find alternative implementation to abstract data types, ADTs. We are used for our day-to-day implementation. As such, ADT is doubly linked list structure. In this article, I present the conventional implementation, the alternative implementation of the doubly linked list. W. Sinha. Now, with insertion, transversal, and deletion operation, I also provide the time to memory measure of each to compare the pros and cons. The alternative implementation is based on the pointer distance. Okay, the alternative implementation is based on pointer difference distance. Sorry, so I call it the pointer distance implementation for the discussion. Each node would carry only one pointer field to transfer the list back and forth. In conventional implementation, we need to keep a forward pointer to the next item on the list and the backward pointer to the previous item, as we do in doubly linked list. We have previous and we have a next. All right. Now, the overhead is 66. All right. This is it. The overhead is 66 of the conventional node and 50% of the pointer distance implementation. We use multi-dimensional building lists such as the dynamic grid, and saving would be even greater. Greater, greater. Now, a detailed discussion on the conventional implementation of building list is not offered here because they are discussed in almost every data structural algorithm book. Okay, internal pointer variable. Okay, now the conventional and the distance point implementation is events used in the same fashion to have comparable memory and time usage statistics. Node definition. We define a node of point distance implementation like this. Okay, we have a T and then we struct list node, that is a T of elm, and the struct node into pointer diff. Okay, we have the list node and we are multiplying this with the pointer node, pointer difference. Okay, the pointer difference point field holds a difference between the pointer to the next node. Wait, the pointer the pointer difference pointer holds the difference between the pointer to the next node and the pointer to the previous node. Okay, now pointer difference is captured by using exclusive OR. That's interesting. Okay, any distance of such list has a start node and an end node. Okay, and now start nodes points to the head of the list and end node points to the tail of the list. That is correct. By definition, the previous node of the start node is null. That is also correct. And the next node of the end node is also null. That is also correct. For the singleton list, both the previous node and the next node are null nodes. So the pointer difference fields holds the okay. Wait, I'm losing it. So the pointer difference fields holds the null pointer. All right, that is one thing. The pointer difference field holds the null pointer in a two node list. In a two node list, the previous node to the start node is null and the next node to the end node is end node and the next node is the end node. The pointer difference of the start node is exclusive of or end node and the null. That's interesting. I don't know how the XOR is working here, but it sounds so cool, man. Like the pointer difference of the start node, the pointer difference of the start node is the exclusive OR of the end node and the null. That sounds so cool. All right. Now, and the pointer difference of the end node is a start node. Okay, transversal. Okay, now the insertion and deletion of the specific node depend on the transversal, and we need to only simple routine to transverse back and forth. If we provide a start node as an argument, and because the previous node is null, how direction of the transversal implicitly is defined to be left to right. On the other hand, we provide the end as an argument and implicitly define the direction of the transversal is right to left. Okay, the present implementation does not support the transfer from the middle to the list, but it should be easy enhancement. The next node defines as follows. Okay, so what are we doing here is the list node. Okay, now the pointer list node, next node is okay. Now I am overwhelmed from this code. I need to move to TypeScript or JavaScript. All right. Okay, now I'm overwhelmed. Okay, I cannot do it more. All right, let's end it here. All right, very good here. And this unrolled linked list. Okay, that is another linked list that is unrolled linked list. Okay, we will study this maybe tomorrow. Okay, and how many linked lists are there? Let's see. This is unrolled linked list, and then we have escape list. Okay, then we have linked list problem solution. Okay, then we will solve the problem and solution. All right, so for today we are ending the stream right now. I hope you are good and fine.